So this is the penultimate video for the second year. Okay, so I'm going to start to share my screen in a second. Okay, let's go and share the screen. There we go. Right. Okay. So so electronic configurations. Okay, we need to make sure we're clear on those. So we need the electronic configurations of these things. So we've got chromium 4s1 3d5. Remember, it has the slightly odd electronic configuration because one of the s electrons is promoted up to 3d to make sure we've got a half full d shell. And therefore in chromium 3+, we're going to lose that S1 and then 2 more to give us 3D3. Copper is also the odd one, so we've got 4S1, 3D10. Copper 2+ is going to lose an S1 and D1, so it ends up being 3D9. Okay, so give two species that are isoelectronic with chromium 3+. Okay, something that's isoelectronic with chromium 3+. Okay, so you can think what those could be. Okay, we'll move on to looking at what we're going to be doing in this lesson, this session. So describe simple precipitation reactions. Now, these are the ones that you need to know. Yeah, copper 2+, chromium 3+, manganese 2+, iron 2+, iron 3+, with hydroxide and ammonia. Okay. And what's happening with ligand substitution in copper 2+ and 3+. Obviously, we've talked about hemoglobin in the last session, but that's just clear about that. And you need to be writing equations for the reactions and recording color changes that take place. And in fact, in practical 27, you'll be doing that ligand substitution practicals with lots of nice color changes. Okay, and also we'll go on to talk about why precipitation reactions actually take place at the end. Okay, so we have got these precipitation reactions and ligand substitution. So formation of a solid from a solution during a chemical reaction, form when two aqueous solutions are mixed together. And ligand substitution is where one ligand is replaced by another. Okay, so you should work through page 35 in your booklet first, and you'll need to read pages 149 to 153 to help. And do it in pencil first, write small, we'll go through them. So, okay, so what you should probably do is to make sure that you stop the video. So stop now. Okay, and come back when you have done those activities. Okay, so we will move on now and get rid of that. Okay, so we're going to move on and okay. So making flashcards. So before we go through the correct answer and explore those reactions in more detail, what we're going to do is suggest that you make a separate set of flashcards just so you learn different colors. And it'd be quite cool if you could use the different colors to do it. So for instance, you could write on one card copper or hexa aqua copper 2. Okay, so in brackets Cu brackets H2O brackets 6 close square brackets 2+. And then on the back of that card, write that it's a blue solution, because you're going to need to learn the colors of some of these solutions that we do in the table that you're going to write out. So formula on one side, color on the other side, and do try to make sure that you write in the same color as the color of the solution, because it's really hard if you change the colors. Remember to say if it's a solution or a precipitate. Okay. One form, one side, color on the reverse. Remember to say if it is solution or precipitate. Okay, right. So let's go through the reactions. So this is when you have done practical 27, you should get results that are similar to this. So we will go through them carefully. So I'll just make them appear one at a time, and you can check them off. Okay, so check off yours as you do them, and then you make these into flashcards. So now we're going to see what happens if we add excess ammonia. Okay, so with some of them we get no reaction, okay, and some of them we do, okay, and underneath each one we've got the actual equation for what's happening. So this is the ligand exchange process. So we can see that if we take, for instance, the iron hexaaqua iron, and then we hexaaqua iron 2, if we add hydroxide, eventually we'll make iron hydroxide solid, okay, and its color will be green, okay, and this only will happen once you have added, you know, it's gone through and replaced all of the aqua ligand. Okay, so we've got yellow becoming orange or orangey brown, okay, and we've got the equations there, and you can see obviously this balances with the redox or the oxidation numbers for we need 2 OH minus with Fe2 plus and 3 with Fe3 plus. So we can do that, we can make our chromium hydroxide, okay, but then we can add excess ammonia and we will get hexaamine chromium 3. Okay, so lovely color change with the copper. We get a nice deep blue when you add ammonia to it. So we have got the equation there, okay, for those. Right, now what happens if we add excess chloride? Okay, so if you add excess chloride to it, it's going to go yellow. And we've got that reaction happening. And same with the copper, we get yellow color and we get that reaction happening. Okay, so it's going to be a good idea for you to write down the ionic equation. So observation with a small amount, okay. So what you're actually going to do is you're going to add the hydroxide, but you can add it slowly, dropwise. Actually, what happens is you get a pale blue precipitate, which then becomes insoluble with further OH minus. So it precipitates when you add hydroxide to it. Iron is pale green in water, and we get an insoluble green precipitate with further OH minus, but it will start to darken because it's going to oxidize to Fe3 plus in the atmosphere. So here we've got yellow solution, that will be orange-brown precipitate, insoluble with further OH minus. The manganate is a pale pink solution, okay, and it will go light brown, okay, but it can, it's insoluble when you put extra OH minus in it. Now, this is interesting. The chromium here is chromium 3 plus, and it's violet. When you've done your oxidation reactions with alcohols, you've seen it goes from orange to green. So green is the +3 state that you see in there. However, you've got sulfate ions in there as well. So this is the sulfate ions because you've done it in acidic conditions with sulfuric acid. There's going to be sulfate ions, and that will mean that this ends up being green rather than violet. Excuse me. Okay, and when you when you add a hydroxide to the chromium, you'll get a grey-green precipitate. But if you keep adding hydroxide, it will then form a dark green solution. Okay, so what has happened here is you've pulled it out of the solution to make it precipitate, but then if you add, and that should be chromium hydroxide with 3 hydroxides to balance out the 3 plus the chromium. But then you can actually stick more hydroxides in, and they will form a hexahydroxy chromium 3 plus, or hexahydroxy chromium 3, which has an overall charge of -3 because we've got 3 of the minuses, 3 of the pluses cancelled out by the hydroxide here, and we've got 3 extra hydroxides. Okay, right. Okay, so and now what we can look at is what happens if we add excess ammonia. So we get a pale blue precipitate. Okay, so this will redissolve and goes pale blue, and then if we add excess ammonia, we then end up with it going deep blue. Okay. Okay, pale green solution with the iron 2. Green precipitate is insoluble with further ammonia. Yellow solution, rusty brown, insoluble with further ammonia. Chromium is violet. Okay, then it's grey green. Manganese is pale pink, and then it is light brown when it's manganese hydroxide. and darkens and is still insoluble with further ammonia, so we're actually not getting much further reaction. Okay, and this is soluble in excess to give a purple solution of chromium 3+. Okay, and we can see the equations there. It's a slightly different layout, possibly from your booklet, but it might be a better way of remembering it. Okay, so let's think about copper, hexa-aqua copper in more detail. Okay, what happens when you add hydroxide to it? Okay, you get a precipitate and a color change. Okay, so it's a blue solution and you get a pale blue precipitate. Notice that this complex is a solid. Okay, that's what's actually happened. And we simplify that to the fact that it just becomes copper hydroxide. Okay, so that's actually what's happening inside the complex. Okay, as it occurs, it's acid base. Okay, and we'll look at that in a bit more detail later on. Okay, what happens if we leave it in air? Okay, well, nothing, because there isn't such an ion as copper 3. The highest oxidation state or preferred oxidation states for copper are 1 and 2, so it won't oxidize further. Okay, and if you compare it to Fe2+, which is easily oxidized to Fe3+ in air, so that one, Fe2+, would change to Fe3+. Okay, what complex ions have we got? If we've got a metal hexa-aqua, and now you see why. Now we're going to go back and see why this is an acid-base reaction. Okay, so if we've got a lone pair from the oxygen being pushed towards the metal, in this case we've drawn ion 3+, they're pulled away from the oxygen towards the 3+ ion, and so that means they're being pulled this way towards the 3+, and that means that this lone pair is pulling electrons that way, which will also mean pull the electrons here away from the hydrogens. So they are normally polar in this direction, so they are normally towards the oxygen, but they're going to be pulled even more if these ones move towards the ions. They'll be pulled even further. Okay, and that means that this delta plus, this hydrogen ion, that delta plus is slightly more positive than normal and could break off quite easily. Okay, so each oxygen has another lone pair. So we've only drawn one lone pair on the water molecule. They've got another one, but if we drew that one, it would make it look a bit, well, even more messy. Okay, so the complex acts as an acid. It can donate a hydrogen, so these hydrogens can come off. Okay, so what's going to be more acidic, a metal 2+ or metal 3+? Well, it's going to be the metal 3+ because that will pull the electrons even more than the metal 2+. Okay, so you know, metal 2+ compared to metal 3+ is going to be less acidic. Metal 3+ is going to be more acidic. So these complexes end up being acidic because they're pulling the electrons away from the oxygen, or the lone pair away from the oxygen, which in turn pulls the electrons in the bonding pairs away. And so these hydrogens are more positive and can break off more easily. Okay. So what happens when we add small amounts of ammonia? It acts as a base. It's going to remove the H+ from the complex until there's a precipitate. Okay, so the hydroxide is blue. Okay, so we've got our hydroxide compound there. We add ammonia, so we've got pale blue solution. Then it goes pale blue precipitate. So yeah, ammonia is a source of OH. Yeah, so it's going to produce OH in solution. Okay, and it's the OH here that you know makes it look a bit like the same thing as that happened when you had hydroxide. Okay, so it's pulling this hydrogen away from the water. Okay, and therefore that's how we get the hydroxide formation here. Okay, so the hydroxides are formed here, one there, and that's because the ammonia comes away and pulls the hydrogen away to make ammonium. Okay, so if we add excess ammonia, it dissolves, and that's because then ammonia actually becomes a ligand. So it's acid base here, yeah, it's acting acid base here, but then when I add excess ammonia, then it becomes a ligand. So we had our copper, our dihydroxy tetra aqua copper 2+ complex. And then if we add the ammonia, it will then go in and kick the hydroxides out and 2 of the waters. So we're then left with tetraamine diaqua copper 2+. okay, which is this one here. And this is a darker blue, a nice dark blue, which dissolves. Okay, so that's soluble. Sorry, that's insoluble. This is soluble. Okay, and so why does this work? Okay, well, I've got one molecule and four molecules. That makes 5 molecules. I've got one molecule and 4 molecules. That also makes 5 molecules. But this is solid. This is aqueous. Okay, so the entropy is greater on the right hand side because we've got aqueous, liquid, aqueous versus solid and aqueous. Okay, so pale blue, deep blue, and hopefully when you do the practical, that will look really, hopefully you get nice results. So overall, if I add 4 ammonia, we're going to get that happening. But be aware that ammonia would cause 2 of the waters from the hex aqua to become OH minus. Okay, so copper and ammonia looks like this. Okay, so first off, we add a small amount of ammonia and we get the hydroxide formed. Okay, and then if we add more, we then get that nice dark blue color. Okay, so the first part is acting as an acid and a base reaction. So the ammonia is the base, the complex is the acid. Okay, and we get this precipitation. And then if we add excess ammonia, then we got a ligand exchange going on. Okay, so we can have a distorted tetrahedral shape because the carbon-oxygen bond is longer than the carbon-nitrogen bond. So we've got a distorted octahedron, and that will give us this shape. So that is going to have a slightly distorted shape. Okay. Right, what happens if we add some chloride? If we add lots of chloride ions to the hexaqua complex, what happens? We actually will push all the hexaquas out and just put 4 tetrachloro in, and that then is a change of shape. We've gone from octahedral to tetrahedral. Okay, and we've gone from 5 molecules to 7 molecules, so it is favored. Okay, so chlorine will displace the water as a ligand. We have a ligand exchange going on, and the entropy is good. Okay, so we've got blue octahedral, yellow octahedral. Okay, what type of reaction is this? Ligand substitution, and we end up with those shapes. Sometimes it looks green rather than yellow. Okay, well, the reason it's going to go green and yellow is because you've got a mixture of blue and yellow, perhaps, so you haven't added enough chloride. Okay, another reaction with iodide, which you'll see when you do practical 31. Iodide can lose electrons in reactions. What kind of reagent are they? If they lose electrons, they are being oxidized. What will I become? It'll become I2. And it will, so they would reduce other things, yeah? So they're being oxidized, they would reduce other things. What happened then react with copper 2? Okay, they're going to reduce it to copper 1. Okay, so we take our copper 2+, we add 4I, we get 2 copper iodide, which is an off-white precipitate, and the iodine is brown. And we've talked about this because we will be doing fly sulfate. Right, so now we're going to have a look at chromium, hexaqua chromium 3. So reactions of it. Okay, chromium ions are typically M3+, the most common ion for them. So aqueous solutions will contain the violet octahedral hexaquachromium 3, okay, which is on the left. And if we add hydroxide to this, we'll get a green precipitate, which is soluble if we add excess ammonia, sodium hydroxide. Okay, so if we add hydroxide, the hydroxide will pull the hydrogen off, okay, and form water molecules, yeah? So we've got a water molecule here, and therefore we're left with hydroxides on here, here, and here. Okay, and now if we add excess hydroxide, precipitate dissolves, and we get a green solution, which is octahedral, which is where all the OH minuses have gone on. And we can see that visually there. Okay, so chromium, okay, if we add ammonia, okay, then we get a green precipitate, and again, it's also soluble if we add excess ammonia. Okay, so first off, we create the hydroxide or the hexahydroxy, sorry, we've actually got the triaqua, so we name it properly, trihydroxy chromium 3. So if we add excess ammonia, that redissolves, okay, so we actually replace all the ligands with ammonia. Okay, and that gives us a purple color. So we have multidentate ligands like hemoglobin. Okay, 4 polypeptide chains, each with a heme group on them. Okay, so hemoglobin has got 4 of those, yeah, and they can pick up oxygen. Okay, there's sort of like a model of the you know, a representation of the protein. So what does it do? Transports oxygen. How does it do this? O2 attached to Fe as a ligand, comes off when needed. Okay, how many O2 can attach? 1 per heme. So actually, we're only getting 1 attaching here. So we're not getting 1 behind. We're only getting 1 attached here. So 1 to the heme. Okay, but because there are 4 of these in the molecule, we can actually carry 4 oxygens per hemoglobin. So carbon monoxide is incomplete combustion, etc. Why is it toxic? It substitutes for oxygen and binds more strongly irreversibly. It's colourless and odourless, so we'd have to use a CO sensor, which is why a lot of the rooms here are fitted with carbon monoxide sensors and carbon dioxide sensors probably, and they will then start the fan systems if the levels get too high. So find out more about hemoglobin and ligand substitution by reading 151 in your textbook. You need to think about the different ways of remembering all the colours. Now this will be a great one with my, to get my daughter to come and do this. I've got, yeah, actually, yes, my new nails. Yeah, I'm going to get my daughter to paint my nails. Okay, you know, this is a good way to do it. Good way to do it now, because then you just remember your nails. What are the rules about nail varnishing? You probably would have to have it removed. Okay, in the exam room anyway. So then there is a chem guide, okay, which links to that. I'll put a link in the presentation for that. So a quick test. Copper hydroxide, what color? Yeah, blue precipitates. Okay, iron 2 hydroxide, green precipitates. Iron 3 is an orangey brown precipitate. Manganese 2 hydroxide, light brown precipitate. And chromium hydroxide is a greyish green precipitate. Okay, so those are, you know, obviously you test yourself on that and test each other on them. Okay, so some aqueous solutions. Copper, hexaqua copper, pale blue. Diaqua tetraamine, dark blue. Yellow. Okay, manganate, well, we know that's purple. Okay, Mn hexaqua manganese 2, colourless or very pale pink. Chromium, we know that is orange. Okay, chromium, hexaqua chromium is violet, sometimes green, and we said it's green because we have sulfate in there, because if we're doing oxidation reactions. Hexahydroxychromium 3, okay, dark green. Hexaaqua chromium 2, pale blue. Okay, so you're going to have to learn these. So yeah, I can just imagine my thumbnails with these atoms labeled with their colors. Yeah. Okay, so where we get to that one, iron, hexaaqua iron 2 is going to be pale green. Hexaaqua iron 3 is going to be pale yellow. Okay, so obviously check those, and that is pretty much it. Obviously you can work through that. This is what we covered. Okay, and yeah, okay, I think we're done.